You know, every single time you stream a movie or you post a photo, you're using a tiny, tiny little slice of a massive, shared computer somewhere out there. But have you ever stopped to think, how did these tech giants safely run millions of totally different applications on the exact same hardware all at the same time? Well, today we are going to deconstruct the cloud to find out just that. Let's dive in.
It really all boils down to this one question. You see, at its heart, cloud computing is just about sharing a massive pool of resources. You know, processors, memory, storage. But sharing is, well, it's complicated. You can't just let everybody's code run wild on the same machine. So how in the world do you slice up that pie safely and efficiently for everyone?
So to really get how we got to where we are today, we're going to follow the evolution of the solutions. First, we'll start with the core challenge of just sharing hardware. Then we'll explore the foundation of it all, virtual machines. After that, we'll look at the lightweight revolution of containers. And finally, the ultimate abstraction, serverless computing. And by the end, you'll know exactly how to choose the right tool for any job.
Okay, so let's start with that fundamental problem. Imagine you've got one giant, powerful physical server, but thousands of different customers who all want their own small, secure piece of it. That is a major, major challenge.
The key word here, the most important word, is isolation. You absolutely need digital walls, thick ones, between every single application. I mean, think about it. If my banking app is running on the same piece of metal as your photo sharing site, they cannot be allowed to see or affect each other. No way. One little crash or one security flaw can't bring down the whole system. This is the problem that kicked off this whole journey.
So the first brilliant solution to this challenge was the virtual machine, or as you'll hear it called, a VM. And the whole concept is right there in the name. You are literally building a complete, self-contained computer, but it's made entirely out of software.
Right. So instead of a physical box with a CPU and RAM that you can actually touch, a VM just emulates all of it. It's like a digital ghost of a real machine. And this is so powerful because it means you can run a full version of Windows on a Linux server, or the other way around, all inside these neat, totally sandboxed environments.
Okay, let's look at how this is actually built. So at the very bottom, you've got the physical hardware, the real machine. On top of that, you have something called a hypervisor, which acts as the manager, carving up all the resources. But here is the most crucial layer. For every single VM, you install a complete, unique guest operating system, a full OS, for every single app. Remember that part.
And this brings us to the biggest advantage of VMs, security. I mean, because each VM is a full, isolated computer with its own operating system, the walls between them are incredibly thick. You can dedicate one VM to be just a web server, another to be a database, and you can lock them down completely. It's basically the digital equivalent of putting each computer in a separate locked room.
Okay, this sounds perfect, right? I mean, complete isolation, maximum security, problem solved. But as with any technology, there are always trade-offs. What's the price we have to pay for all of this amazing security?
Well, the downside is their weight. And when I say weight, I mean resources. Remember how each VM needs its own full operating system? Well, that OS eats up a ton of CPU, RAM, and storage space before you even install your actual application. It's kind of like buying an entire house just so you can use one room. Yeah, it's secure, but it is not very efficient.
And that's exactly what led to the next big evolution, the container. The whole goal here was to get those great isolation benefits of a VM, but without that massive overhead of running a full operating system for every single little app. And this right here brilliantly illustrates the fundamental difference. This is the key. A VM tricks an operating system into thinking it has its own physical computer. A container, on the other hand, tricks an application into thinking it has its own operating system. It's a much higher, much more efficient level of abstraction. So, let's look at the stack again. See what's missing. There's no guest OS. Instead, all the containers share one single host operating system. The container engine is the new manager, sitting between the apps and that shared OS. And this efficiency? It translates directly into what you experience every day. Websites that load faster, apps that respond instantly, all because less power is being wasted. So the whole process becomes incredibly simple and portable. You just package up your application with only the specific bits of code and libraries it needs to run, nothing extra. Then that little container can run on any machine that has a compatible container engine, whether that's your laptop or a giant cloud server.
All right, so let's put them side by side.
VMs, they give you that fortress-like security and isolation, but you pay for it by them being heavy and slow to start up. Containers are incredibly lightweight, fast, and portable, but they do come with a new risk. Since they all share an operating system, a vulnerability in that shared layer could, potentially, affect all the containers running on.
And that brings us to the next evolution. What if? What if we could abstract things even further? I mean, forget managing an operating system or a container. What if you only had to worry about your code and absolutely nothing else? Well, that is the promise of serverless.
Now, to understand serverless, we first need to see how apps themselves have changed. We've moved from these monolithic apps, basically one giant block of code, to microservices, where a big application is broken down into tiny independent functions. This change is the reason your favorite app can update just one feature, like its search bar, without you having to reinstall the entire thing.
And serverless, which is also called function as a service, is, well, it's exactly what it sounds like. As a developer, you write a small piece of code to do one specific task, like resize an image or process a payment. You upload that single function to the cloud, and the provider takes care of everything else. You never have to think about servers or operating systems or even containers.
But here is the most revolutionary part. With VMs and containers, you pay for them as long as they're running 24/7. With serverless, you are only charged for the exact milliseconds your code is actually executing. So, if nobody is using your function, the cost to you is zero, a big fat zero. This is what allows a tiny startup to build an app that can handle millions of users overnight without a massive upfront cost.
So we've gone from a full digital computer to a lightweight application package to just a single, tiny function. So the big question is, which one's best? But see, that's the wrong question. It's not a competition. It's about having a toolbox and picking the right tool for the job, constantly balancing that trade-off between isolation and efficiency.
This slide right here, this sums it up perfectly. Think of it as your cheat sheet. Do you need to run an old monolithic application? Or do you require the absolute highest level of security? A virtual machine is your best bet. Are you building a modern app with microservices that needs to be portable and scalable? Containers are the industry standard, no question. Do you have a specific task that only runs once in a while? Well, serverless is going to give you incredible cost savings and simplicity. So we've moved from managing hardware to managing operating systems to managing applications to managing just single functions. Each step gives us more power and more efficiency by hiding the complexity below it. So the final question to think about is, what's next? What's the next layer of complexity that we're going to make invisible in our relentless pursuit of efficiency?